Hello and welcome to this lecture. In the previous lectures, we went into details of definition of eigenvalue, eigenvector. How do you compute it given a matrix and what it means and all that. So in this, and what the computation means, I mean, how do you find the eigenvalues from the characteristic polynomial, algebraically solving them? How do you find the eigenvector for every eigenvalue and what all can happen? I mean, you get certain number of repetitions for the eigenvalue in the characteristic polynomial as root, algebraic multiplicity, and then you get a certain number of linearly independent eigenvectors for a minus lambda I, the null space, in the null space of that. So how are these two related? We went through various examples on how different possibilities arise. I hope that part is clear. As you get more practice, it will become clearer. Now, there are a few interesting properties. I mentioned them here and there, but I didn't quite prove them. So we'll see a few proofs and understanding of some properties. And also, I've used the language of matrices primarily to keep things simple. But if you look at proper linear algebraic treatments of eigenvalue, eigenvector, people will use the operator language. So an operator can have multiple matrices in different bases, and the eigenvalues remain the same, and the eigenvectors have some connections, etc. These are important things, and I'll mention that also in this set of properties. So let's get started. So the first thing, before we get started, we used a lot of polynomials and roots. I mentioned some results from that. I want to put them in a clear setting so that we are clear what I'm talking about, because we haven't discussed this much in this lecture. So I wanted to just write a few facts about it. Many of this might be well known to you, but just a quick repetition so we are sure. We saw already from the fundamental theorem of algebra, if you have an n degree polynomial with complex coefficients, there are n complex roots counting multiplicity. So this is one of the important facts. We are not going to prove this in this class, at least. It needs more advanced techniques. But what this means for us is the number of distinct eigenvalues of an n by n matrix is less than or equal to n. I say distinct here. Total number of eigenvalues counting multiplicities will be equal to n. But number of distinct ones will be less than or equal to n. Some of them can repeat more than once. So this is what this means. Here are some examples just to give you complex coefficient polynomial, and then the factors like this. And then you can see there are 3 roots, multiplicity 1 each. Here is another polynomial which factors, and you see here there are 3 distinct roots. One of them has multiplicity 2 adding up to 4, and degree is 4 here. So it's just examples. There are tools, computer packages which will do all this. We've seen that already. Okay, so that's just one example. There's one connection between roots and factoring. This was implicitly used. I didn't really prove it. I wanted to do a proof for that. Supposing you have a polynomial f of x, degree n polynomial, and then alpha is a root of this polynomial. What does that mean? It's f of alpha is 0. That's what it means. So it turns out if alpha is the root, you can write f of x as x minus alpha times a n minus 1 degree polynomial. Okay, so notice what has happened here. This is called the factoring result. So if you have a root, you can factor out a linear factor, x minus alpha factor, which now you can see if you plug in alpha, right, this becomes 0. So this whole product becomes 0. Of course, alpha may be a root of this also. We don't know, but at least x minus alpha is possible, right? So this is a fact, and you can prove, I'll give you one proof. There are many ways of proving this. One proof is to explicitly find the b, right? So you know f of x, meaning you know all these coefficients. A is you know, and you know alpha. Given a, the coefficients a and alpha, can you find the b consistently? If you can find the b consistently, then you're done, right? So that's the way in which I'm going to do the proof. I won't do it in great detail. I'll just quickly write it down. You'll see how to do it. The way to do it is to simplify the right hand side. You will, if you cross multiply and then add it all up, and not cross multiply, just multiply every term by term and then add it all up. You see x bar n will show up, and then there'll be 2 terms for x bar n minus 1, right? X into this guy will give you x bar n minus 1. Alpha into this x bar n minus 1 will give you x bar n minus 1. So you have 2 such things. Till you go to x, you have 2. And then finally, you will have a constant, which is only 1 term minus alpha b naught. So this is the product on the right hand side. I want this to be equal to f of x coefficient wise. Coefficient by coefficient, these two have to be equal. If that has to happen, so you see bn minus 2 minus alpha is the coefficient of x bar n minus 1. The coefficient of x bar n minus 1 is a n minus 1. So bn minus 2 better be equal to alpha plus a n minus 1. Okay, only then the coefficient of x bar n minus 1 will match. So you found b n minus 2. So this way you find every b. So you find b n minus 2 like this, and then you find b n minus 3, which has to be alpha b n minus 2 plus a n minus 2. You know already what b n minus 2 is. You plug in, you find b n minus 3, you find b n minus 4. Likewise, you can go all the way and find up to b0, right? b0 will come from the coefficient of x term. But guess what? The coefficient of the 0 term, the constant term, also should match. So for that I need a naught to be equal to minus alpha b naught, right? So our 0 should be equal to this, and that ends up being the same as f of alpha being 0. So this is a quick way to verify. I'm not doing it in great detail. You can read this again slowly for you to understand. So basically, when you have a root, you can also factor out a linear factor. So this is a fact, and we have used this repeatedly. So for instance, fundamental theorem of algebra says a complex coefficient polynomial has a complex root. Once you have a complex root, you factor that out. So you have a degree n minus 1, then you find the root again. So that way, factorization into individual linear factors is possible, and that's what we used, for instance, when we wrote polynomial equals, lambda minus lambda 1 power a1 into lambda minus lambda 2 power a2. You can always write a polynomial like that. Of course, complex is very important. If you say real, this won't work. Complex, you can do this, and that's the fact here. Okay, so I didn't prove it, just for completeness I'm doing it. This is one of the first properties we'll see. Okay. Now, when a polynomial has real coefficients, some additional things will also happen, right? If you have a real coefficient, it turns out complex roots occur in conjugate pairs. So if you have alpha being a root, a plus bi, then alpha bar, you can see the bar faintly here, which is the complex conjugate, is a minus bi is also a root. It's very easy to prove, right? The polynomial f of alpha is 0, and then you conjugate. Because the real coefficients don't change, only the alpha changes, and the powers are consistent, so you get that. So degree 1, if you have a degree 1 polynomial with real coefficients, there will be only one real root. If you have degree 2, you can have one real root of multiplicity 2, two real roots multiplicity 1 each, or two complex roots multiplicity 1 each, right? So all these three are possibility for a quadratic polynomial. For a cubic polynomial, notice what happens. You can have one real root with multiplicity 3, two real roots with multiplicities 1 and 2 each, or you can have one real root with two complex roots, and these two complex roots being conjugates of each other. Remember, real coefficients is important, so multiplicity 1 each. So these are the possibilities for 1, 2, 3. So that's why I said degree 3, you always will have at least one real root, okay, and so on. You can look at other cases and do. Degree 4, you need not have any real root, by the way. So, but degree 3, you will have at least one real root. In fact, any odd degree, you will have at least one real root. See, these are all facts about polynomials and roots, and this big list of problems there in these areas. But this is not of our interest, but when we do the characteristic polynomial solution, some of these facts are important to us. I just wanted to complete this. Okay. Now let's move on to another very important property I stated but didn't prove. This is the eigenvector independence property. I think we did this maybe in the R2 case, I'm not sure, but anyway, so this one is a very important property. So let's say you have two eigenvectors, of course they're clearly non-zero, and corresponding to two different eigenvalues. V1 is an eigenvector with eigenvalue lambda 1, V2 is an eigenvector with eigenvalue lambda 2. If lambda 1 not equal to lambda 2, V1 and V2 are linearly independent. This is a powerful property, right? So if you have eigenvectors of corresponding to two different eigenvalues, those two eigenvectors have to be independent. Okay, so that's linearly independent meaning. Okay, so basically that's the thing. Eigenvectors of distinct eigenvalues are linearly independent. I've written it for 2, but you can push it for more than 2. If you have 3 distinct eigenvectors, the eigenvalues, 3 distinct eigenvalues, the eigenvectors corresponding to the 3 distinct eigenvalues will be linearly independent. Okay, that's a very nice fact to have. Proof is actually very easy. The proof goes by sort of like contradiction. So the way you prove linear independence is like this, right? Suppose that they are not linearly independent, right? So let's say there is AB such that AV1 plus BV2 equal to 0. If this were true for non-zero AB, then V1 and V2 are linearly dependent. Okay, what I will show is you start with this and show A equals 0, B equals 0. If this is true, if AV1 plus BV2 equal to 0 is true, then A is 0, B is 0. Okay, that is the definition of linear independence, isn't it? So let's see if that is true. So AV1 plus BV2 is 0. Let's say you start with that. Then what happens? You act with A on both sides. Okay, so when you multiply with A on the left, okay, you get A times AV1 plus BV2, but then that is what? Small a times capital A V1. But V1 is an eigenvector with eigenvalue lambda 1. So AV1, capital A V1 is actually lambda 1 V1. Likewise, capital A V2 is lambda 2 V2. So you get A lambda 1 V1 plus B lambda 2 V2 is also 0. So if AV1 plus BV2 is 0, A lambda 1 V1 plus B lambda 2 V2 is 0. So now you can eliminate. You eliminate one of V1 or V2, whichever is your favorite, you can eliminate. Or whichever you don't like, you can eliminate. So here I have eliminated V2. So multiplied the first equation by lambda 2 and subtracted the second equation from it. So you end up getting A times lambda 2 minus lambda 1 into V1 is 0. Okay. Now lambda 1 and lambda 2 are not equal. So this term is not 0 and V1 is also not 0. So if A times this has to be 0, then A has to be 0. Okay. So similarly, the very similar one, if you eliminate lambda 1 from these two, you will get B is 0. So anytime A V1 plus B V2 is 0, A is 0, B is 0, which means V1 and V2 are linearly independent. So this is a very powerful property and we've used it multiple times. Let me show you where I used it. Let's start with the general matrix A and cross N matrix. It's got a characteristic polynomial, it's got R distinct eigenvalues, each with multiplicity A1, A2 to AR, etc. A1 plus AR is N. Okay. Now we know that the eigenvalues have geometric multiplicities B1 to BR, and we know that so B1 to BR are the geometric multiplicities, and we know B1 is between 1 and A1 and so on, right. So we know these geometric multiplicities are possible, but if you look at it, if you look at a linearly independent list of eigenvectors, first for lambda 1 you will have B1 linearly independent eigenvectors, U1 to UB1, these are all linearly independent. Now for lambda 2 you will get B2 linearly independent eigenvectors, right. So now I can number this from UB1 plus 1 to UB1 plus B2 and claim that all these guys, B1 plus B2 of these, are actually linearly independent. Why? Within this they are linearly independent. Now across these two, right, any two vectors are linearly independent, right, because this one has eigenvalue lambda 1 and lambda 2 is different from lambda 1, and this has an eigenvalue somewhere here. So any vector here and any vector here are going to be linearly independent, any set of vectors also. So if you have a linear combination of here being 0, then you can show that all the coefficients will have to be 0. So this entire set is going to become linearly independent. Think about that. You can write down and clearly prove it, and you will get the answer. Okay. So that's the linear independence across this set. So likewise, you can go on and on and on till the last point. So now all these geometric multiplicities B1 plus B2 plus BR add up to M. Okay. So you will go up to M linearly independent eigenvectors. All of these eigenvectors across the distinct eigenvalues, they are all going to be linearly independent. Within the particular eigenvalue, you have geometric multiplicity number of linearly independent eigenvectors. Across the distinct eigenvalues, you can put all of them together and guess what? You still have your linear independence. So that is a powerful result. So if you add up all the geometric multiplicities, that many number of linearly independent eigenvectors you will have. So if you say how many, then this BI, each of the BIs are going to lie between 1 and AI, and then if you add up all of them, you see on the left hand side you will get R, you add up the BI, you get M, you add up the AI, you get N. So how many linearly independent eigenvectors are you going to have? It's going to lie between R and N. What is R? R is the number of distinct eigenvalues. If you have R distinct eigenvalues, corresponding to each eigenvalue, you will have at least one eigenvector, and all of them will be linearly independent. So R is the minimum number of linearly independent eigenvectors you will have. What is R? R is the number of distinct eigenvalues. What is the maximum number of linearly independent eigenvectors? That is N. Okay, that N will happen if every BI equals AI. If every BI equals AI, then M will be equal to N, and you will have the maximum number of linearly independent eigenvectors. Okay, so that having maximal number of linearly independent eigenvectors is very useful. We will see later on when we study diagonalization. Okay, so this is a good way to put all these things together. The linear independence property across distinct eigenvalues is very useful in this particular way. Okay. Alright, so now next interesting property is sum and product of eigenvalues. So to understand sum and product of eigenvalues, let's make this definition. Here is a matrix A. Now it's got various different types of elements. The diagonal elements are interesting. In particular, there is a quantity called trace. Okay, trace is basically sum of all its diagonal elements. So if you add up all the diagonal elements here, right, you're going to get trace. This is called the trace. Okay, A11 plus A22. This trace plays an important role. You'll see the important role it plays shortly. But it turns out sum and product of eigenvalues are interesting quantities for the matrix. You will see what the interesting quantity is. Now this goes back to our previous way in which we defined the characteristic polynomial. If you remember, the characteristic polynomial a minus lambda I is the determinant of a minus lambda I is a characteristic polynomial. That's how we defined it. But we had a way of expanding it out, and we saw that it is equal to minus lambda per n plus the trace, right? What is this quantity? A11 plus A22 plus so on till a and n. This is the trace, plus trace of the matrix times minus lambda power n minus 1, plus then you have lower power terms like lambda power n minus 2 possibly and lower. Okay. So that's the polynomial, that's the characteristic polynomial. This is the form of the characteristic polynomial. Then what did we do to find the eigenvalues? We factored the characteristic polynomial. When we factored the characteristic polynomial, we got n eigenvalues, possibly including multiplicity. Some repetitions may be there, but then we got the n eigenvalues, right? So lambda 1 minus lambda, lambda 2 minus lambda. So the same determinant a minus lambda I can be expressed like in the first way, right? Minus lambda per n plus trace into minus lambda per n minus 1 plus lower order terms. And the same polynomial can also be written as lambda 1 minus lambda into lambda 2 minus lambda so on till lambda n minus lambda. That's how we factor, right? That's also possible. This guy, if I expand out, forget about the first part, the second part, this factored part, if I expand out, what will I get? I get minus lambda per n, it agrees with the first term. Then I get plus sum of all the lambdas times minus lambda per n minus 1. Sum of all the eigenvalues plus lower power terms in lambda. Okay. So notice how the same characteristic polynomial can be written in three different ways. First, in terms of powers of lambda, lambda power n minus 1, lambda power minus lambda power n minus 1. But then we observe this interesting fact that trace shows up as the coefficient of minus lambda power n minus 1. And then when you factor it out, you can write as a product like this. Now in particular, when you expand the product, you see that you have minus lambda power n and then plus sum of all the eigenvalues, lambda 1 plus lambda n times minus lambda power n minus 1. Now you can start making some conclusions. The first conclusion is you put lambda equals 0. If you put lambda equals 0, on the left hand side you get determinant A. On the right hand side you have three different expressions. The second expression is the most interesting for putting lambda equals 0. Because when you put lambda equals 0, in the second expression you get product of the eigenvalues, lambda 1, lambda 2, so on till lambda n. Okay. So what is the product of the eigenvalues of a matrix? It's equal to the determinant of the matrix. Okay. So this gives a lot of side results, like for instance, when is 0 an eigenvalue? If you have an eigenvalue 0, what does that mean? It means determinant is 0. If determinant is 0, what does that mean? It means A is singular. So only when you have a non-trivial null space, you can have a 0 eigenvalue. That's also very clear, right? When you have a 0 eigenvalue, you have AV equals lambda V. When lambda is 0, AV is 0 and V is non-zero, which means A has to be singular. So, a lot of ways in which you can tie up all these properties to derive useful results that we want. The other interesting thing is compare the lambda power n minus 1 terms, of course minus lambda power n minus 1 terms, and that immediately tells you trace equals sum of the eigenvalues, right? Sum of the eigenvalues is a trace, product of the eigenvalues is a determinant. Okay. So, these are very useful properties to have. Quite often you can use these properties to even find eigenvalues, right. So, you may find 2 eigenvalues and you may want the third eigenvalue, but then trace is easy to calculate. So, you know trace is equal to the sum, so you find the other two. Okay. So, these relationships are crucial quite often in some shortcuts for finding eigenvalues and properties of matrices. Okay. So, this is sum and product. Next comes a very, very important idea. This is sort of slightly theoretical in flavor, but if you know this idea, quite often many problems become simpler. Okay, so let me try and explain it. So we're going to start with an operator T and then think of the matrix A with respect to canonical basis representing T. So this is always the picture, we've always had this picture in mind, but then what happens is, supposing you have an invertible matrix S, any invertible matrix S, its columns form a basis. Now, if you want to think of the same operator T in the basis formed by the columns of S and not just the canonical basis, it turns out the matrix that represents T in this basis is S inverse AS. Okay. So, this is called the similarity transform. We have seen it in multiple places. So, whenever you have an invertible matrix S, you go from A to S inverse AS, the operator remains the same, the basis changes, and the matrix changes. Okay, so this is a very important idea. So A and S inverse AS in some sense represent the same operator. They don't represent different operators. So some properties of the operator should not change just because you went from A to S inverse AS. Okay, for instance, determinant of A. Okay, determinant of S inverse AS and determinant of A are exactly the same. Why? Because determinant of AB is determinant of A into determinant of B. Determinant of S inverse is 1 by determinant of S. So determinant of S inverse AS simply becomes determinant of A. So you see, for instance, determinant of A, determinant is actually an operator property. Just because you change from A to S inverse AS, determinant does not change. So you can think of determinant as an operator property. Like that, anything that does not change under the similarity transform, remains the same under the similarity transform, is said to be an operator property and not just a matrix property. When you think in terms of operators, operators property become very interesting, and then a lot of legwork can be avoided if you can identify these things. Okay, so here is a very interesting connection. Look at this. S inverse AS minus lambda I. Why am I thinking of S inverse AA minus lambda I? Supposing I want to find the eigenvalues of S inverse AS. Okay. Now, if you want to find the eigenvalues of S inverse AS, what should you do? You should look at the matrix S inverse AS minus lambda I, right? Now, notice this interesting factorization. I can write the same matrix as S inverse times A minus lambda I times S. So, notice what I have done. I have sort of taken the lambda I common inside in some sense, but it's okay because when I multiply it out, I'm going to get S inverse AS, and then I will get S inverse lambda I S, but that is the same as lambda times S inverse S, but S inverse S is I. So I get the same thing here, that S inverse S sort of cancels. Now because of this, what happens is, if you take determinant on the left hand side, which is what you have to do for the characteristic polynomial, right? If you're finding eigenvalues of S inverse AS, you have to find the characteristic polynomial, and to find the characteristic polynomial, you have to do determinant of S inverse AS minus lambda I. That is the same as determinant of S inverse times determinant of A minus lambda I times determinant of S. So notice what happens to determinant of S. These things are numbers now, right? What is determinant of S inverse? It's 1 by determinant of S, and that will cancel with this, and you get this wonderful relationship. The determinant of S inverse AS minus lambda I is the same as determinant of A minus lambda I. Now this has huge implications. Why? What this means is characteristic polynomial of A and characteristic polynomial of S inverse AS for any invertible matrix S coincide. They are exactly the same polynomial. So what does that mean? Their roots will also be exactly the same. So what that means is the eigenvalues of A and the eigenvalues of S inverse AS are identical. They are the exact same eigenvalues with the exact same algebraic multiplicities because the characteristic polynomials are exactly the same. So what this means is eigenvalue is an operator property. Just like determinant is an operator property, clearly eigenvalues itself are an operator property. And what do we know? Product of the eigenvalue is the determinant. So determinant will also be an operator property, but that also you can prove more directly using the product of the determinant method. Okay, so this is an important fact to remember. Eigenvalue becomes an operator property. A and S inverse AS have identical sets of eigenvalues, including multiplicities. They are the same. Okay, so clearly determinant and trace also become operator properties. So if you have a matrix, the determinant and the trace, in particular the sum of the diagonal elements, does not change whether you do A or S inverse AS. It remains exactly the same. Okay, so it's a powerful property to keep in mind. Moreover, the eigenvectors of A and eigenvectors of S inverse AS are also related, and their relationship can also be very easily found. Supposing you have eigenvector V for A with eigenvalue lambda. Okay, now what happens here? You have AV equals lambda V, right? So this is something that you have. Okay, now this AV I can also write as S inverse V. Okay, I have introduced this S inverse, which is actually identity. It doesn't do anything, right? It's the same. But once I introduce this, notice what happens. I can multiply by S inverse on both sides. So I have S inverse AS times S inverse V is the same as lambda times S inverse V. Now this is an eigenvalue eigenvector equation for S inverse AS. So you block this X inverse AS together, then you have an eigenvector eigenvalue equation. So basically you see, if you have an eigenvector V for A with eigenvalue lambda, eigenvector S inverse V you get for S inverse AS with eigenvalue lambda. Same eigenvalue The eigenvectors go through a very simple translation. You go from V in A to S inverse V for S inverse AS. So this is an important idea. So slightly more abstract. So if you notice, we talk about linear transformations and operators in an abstract way as opposed to matrix, right? M cross N matrix and N cross N matrix. The reason is, this is the reason. As you go from matrix to matrix representing the same operator, many properties don't change. So those properties you have to study as operator properties and linear transformation properties as opposed to matrix properties. Then that gives you some more clear understanding and control over the idea. But granted, this is a slightly more complex idea, but as you progress further, you may appreciate these kind of ideas further. But under the similarity transform, eigenvalues don't change. Eigenvectors have a very obvious transformation, and determinant, trace and things like that don't change. Okay, so this is, I believe, the last property we are saying. Hope you got a better idea and feel for how these eigenvalues operate, and later on in some additional lectures we'll see how these properties can be used to make your work of computing eigenvalues and eigenvectors a bit easier. Okay, thank you very much.